Okay, so what we're going to do here is evaluate conservation of mass in the context of a differential form. And what we're going to do is a little bit different than what we had talked about earlier, and that's instead of using vector calculus, we're going to go from a conservation of mass and a control volume assessment and evaluated a differential element to show the same kind of the same equation set. So what we have here is an arbitrarily small differential element. It has dimensions delta x by delta y, and it is delta z into the page. And we're only going to evaluate this in 2D. So what we can do is put together an arbitrary row. Well, let's just start from one thing. So what we want to do is evaluate our control volume method, which says that the change of density in this control volume is equal to, plus flux of mass through the control volume equals 0. So the first thing we need to do is evaluate the fluxes. And here, we can make this an arbitrary flux. We could say that this equals rho times u times delta y, the height of this element, times delta z. And what we want to do is understand what is the value on the right side. And how we get there is this Taylor series. Which says that you could represent any function by its value at x naught. So x naught is going to be here. This is going to be x. So we represent the value at x, naught, plus its derivative at x naught times the distance, x minus x naught, which is delta x, times its second derivative over to 2 factorial times delta x minus x naught squared. So in the context of what we're doing, we're going to actually take this control volume to the limit. We want to take a limit where delta x and delta y approach 0. And when doing that, these terms go to 0 and higher, and they become essentially higher order terms. These terms approach 0 this term specifically approaches 0 much faster than this one because it's squared. So what we get to do with this is focus on this expansion in the context of this term. So if we want to evaluate the flux, so this is the flux on the left side, the flux on the right side is going to be bracket rho u plus the partial of rho u dx plus higher order terms times the area, delta y, delta z. So this gets us our flux, our mass flux in the axial direction. Now we need to do this for the vertical direction. So we have this term. Here this flux is going to be rho times v times delta x delta z. Again, this is our area. This is the vertical, essentially the vertical flux. And similar to before, we're going to have rho v plus times delta y plus higher order terms, delta x, delta z. Just a comment right here, I missed a term. Here we need to put a delta x there, right? Not that term. So what we do is start plugging it into these equations. One thing I'm going to do is say as delta x approaches 0 and delta y approaches 0, the integral this is approximately true. We're approaching such a small value, the average, that this value is approximately constant. Equals 0 dt x delta y delta z. That's the volume of our little control volume. That's an evaluation of 1. 2 is all these fluxes that we just computed. So let's start plugging them in. So term 1, we have delta x delta y delta z plus, let's do the axial direction first. So we're going to start off with this term. It's positive because it's out. So rho u plus d rho u dx delta x delta y delta z. And we have a negative term, which is rho u delta y delta z. Then we have the vertical terms, which are rho v plus partial rho v partial y delta y x delta z minus the flux into the system, which is rho v delta x delta z. All these are going to equal 0. So just to recap, this term is given here. This term is given here. This term is given here. And this term is given there, which is applied here. So all we have to do is simplify. One thing that you'll see is this rho v delta x delta y cancels out with this. Rho u delta y delta z cancels out with this term. Oops, don't get rid of that. And you end up with rho, partial rho with respect to t, delta x delta y delta z plus partial rho u partial x delta y delta z plus partial rho v dy delta x delta y delta z equals 0. Divide through by our delta volume. End up with conservation of mass which is applied or derived from a slightly different method, purely through applying conservation of momentum. So I just wanted to show you this is from a different perspective, and which I think is very useful.